All right, guys. So we are going to look a little bit at Le Chatelier's principle. This we look at when we have a system at equilibrium and some sort of change occurs to that system. How does the system regain equilibrium is what we're going to be looking at. So we say that if a stress is applied to a system at equilibrium, equilibrium will shift to relieve the stress. So if we add something to the reaction or take it away, equilibrium will shift either towards the reactants or towards the products to reestablish that equilibrium. So for example, here we have nitrogen and hydrogen producing ammonia. Oops. And we look at if we add products, how does that affect the position of the equilibrium? If we add reactants, how does that affect equilibrium? So remember when we were looking at reaction quotient, we said that if Q is equal to K, we are at equilibrium. Anything that changes Q or K will change equilibrium. So Q can be changed by the pressure or the concentration or temperature, and K can be changed by temperature. So as you know, only one thing changes the value of K, and that's temperature. So Q can be affected by pressure, temperature, or concentration. K is only changed by the temperature. So like I said, we're looking at for changes in concentration, changes in temperature, or change in volume and or pressure. Because remember, volume and pressure from gas laws are related. And we're going to look at how these affect the equilibrium position overall. So using our same reaction of the nitrogen hydrogen producing ammonia, oops, excuse me, I hit the wrong button. So we're going to look at what happens if you add a reactant. So how you want to think about this is think about if we had an old time scale, and excuse my drawing, y'all know I can't draw. But here we have the old time scale that has two plates attached as like a counterweight. If we add reactant, we add too much on that left side, we end up with one plate being much lower than the other plate. That is not at equilibrium because our plates are not balanced. So in order to reestablish equilibrium, we would have to shift towards the product side. So we would have to add more of the product in order to rebalance out the two parts of that scale. Same kind of thing if we added a product. If we have the two parts of the scale, we put too much on the product side, there needs to be more on the reactant side to balance them out, so it will shift to the left and make more reactant to balance out. Same kind of thing applies with removing a reactant. If we take away a reactant, then the products are too heavy, so we have to make more reactants to fill in whatever we lost. And if we remove a product, that means that the product side is less than our reactant side, so we need more products for them to equal out. Oops. As a general rule, if you adding shifts to the opposite side, of the reaction, it's like whenever we added reactant, it went towards the products. When we added product, it went towards reactant. So adding is going to shift equilibrium toward whatever the opposite side of the reaction is from what we added. Removing is going to shift to the same side. So if we take away reactant, we have to replace what we removed. If we take away product, we have to replace what we removed. So it will go towards that product side. All right, so let's look at what happens when we're changing temperature instead of concentration or amount. And with temperature, you have to pay attention to what side of the reaction the heat or temperature is being added to. So if we have an exothermic reaction, heat is going to be a product because it is producing heat. So we look at what happens if we add heat. This is going to follow the same rule as concentration. We added heat to the product side. So when we add, we have to shift to the opposite side. So by adding heat, we have too much on the product side. So equilibrium has to shift towards the left, shift towards the reactant side. And what that's going to do, because temperature can change our K value, the overall reaction shifts left. And because we have less product, remember products are on top of our K equation, it's going to result in a smaller K value. So that's why the Ks are affected by temperature, because it's changing the amounts of everything. Now, in that same exothermic reaction, if heat is removed and taken away, remember we said if you remove something, you have to replace it. So if we take away heat in an exothermic reaction, it would shift towards the direction that heat's on, so towards the products to replace that heat. The reaction shifts towards the right. There's more products when we're shifting towards that direction, so that would result in a larger K value. Now, if a reaction is endothermic, so endothermic reactions, you're absorbing heat, so heat is on the reactant side. And same kind of deal. If we add heat, when you add, you go to the opposite side. So we are going to shift towards the right, which is going to make more products, which makes our K value larger. If we're an endothermic reaction and we remove heat, we have to shift in order to replace what we took away. So this will shift towards the left. We're going to have more reactants, less products, which results in a smaller K value. So the general rule for concentration and temperature is whenever you add or increase the amount of something, equilibrium is going to shift to the opposite side of the reaction. If you decrease or remove something from the reaction, equilibrium shifts towards that same side of the reaction to replace what you removed. So remember we said exothermic reactions, heat is a product. Endothermic reactions, heat is a reactant. And like we said, it always goes to the opposite side. So if we increase the temperature in an exothermic where heat is product, it shifted towards the reactants. If we decrease temperature, it shifted to replace that heat and shifted towards the products. And the opposite is true for endothermic. They flip directions because the heat is on different parts of the equation. This is just kind of showing you why this works. We have not talked about free energy or delta G yet, but that middle part at the bottom is where we're going to be at equilibrium. So if we have too much, or if we have an exothermic reaction, there's more heat on that product side, it shifts the actual position of equilibrium. So the graph actually moves over. Now, the one that can tend to be trickier because it doesn't necessarily have the same pattern as the other two changes is if we're changing volume or pressure. So I'll use our same reaction of nitrogen, hydrogen producing ammonia. And here we have a picture of a piston. So a piston is an enclosed container where the top can push in or pull out. So it can decrease the volume, which increases the pressure, or it could increase the volume, which decreases the pressure. So here it's saying that we are pushing down on the piston, which means that we are, we are decreasing volume, which increases pressure. We are forcing those particles closer together. So if you look at what we have here, we have 1 nitrogen, 3 hydrogen producing 2 ammonia. If we look at what is inside of our piston, if we look at what is inside of our piston, there are 2 nitrogens, 5 hydrogens, and 1, 2, 3, 4, 5 ammonia. So if you notice on our reactant side, we have 7 moles of gas. On our product side, we have 5 moles of gas. So notice that the side that has more is our reactant side. Excuse me, I'm going backwards on this. That does have more moles of gas. But if you look at, in terms of our mole ratio, where it was like a 4:2 ratio, now it's a 7:5 ratio. There are more products. There are more products. So whenever we increase the pressure, it goes to the side with less moles of gas. So notice that whenever we increase the pressure on the piston, there are more gas particles that were created. So it's a higher ratio of products, which has that lower moles of gas. All right, so then here, notice that the piston is expanded. We pulled up on that lid, which is going to increase the volume and decrease the pressure. So here you'll notice there are 3 nitrogens inside. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens and 3 ammonia. So notice that whenever we look at the ratio, we now have 11 moles of gas compared to 3 moles of gas. Where it was a 2-to-1 ratio, now there is more of a ratio of reactants to products. And that is because when we decrease pressure, we shift to side with more moles. Of gas. Because there's room for more particles, so it produces more particles. This is the one that tends to trip people up, but it's always the opposite. If you increase pressure, you go to the side with less moles of gas. And we only look at the moles of gas. If there's something else there, we do not count it in our number of moles. If you decrease the pressure, you go to the side with more moles of gas. All right, so kind of summarizing that together, we said if you increase the pressure, you shift to the side of equilibrium that has less moles of gas. If we decrease the pressure, we're going to shift to the side of equilibrium with more moles of gas. One thing to take into account, because we know that some reactions occur with a catalyst. So looking at what a catalyst does, so remember, catalysts lower that activation energy, which makes the reaction go faster overall, because you're going to need less collisions and less energy to make products. Catalysts have no effect on the equilibrium position though. So if you add a catalyst, it does not change where equilibrium is. So it'll affect the rate of the reactions, but it affects the forward and reverse reactions equally. So equilibrium does not change. So let's look at some of these shifts in equilibrium and what this is going to, which direction these will shift. So here we have the reaction of PCl3 and chlorine producing PCl5. And it tells us that our heat of the reaction is negative 88 kilojoules. So remember, that means that this is exothermic. So heat is going to be a product. So I'm just going to put heat on that product side for us to see. So here it just wants to know in which direction does the equilibrium shift when these different stressors occur. It's simply looking at either left or right, towards the products, towards the reactants. So if PCl3 is added, we're adding to our reactant side. Remember, we said when it adds, it shifts towards the opposite side. So if we add on the reactant side, we shift toward the product side. For the PCl5, when it is added, we are adding a product. Adding, you shift to the opposite side. So we're going to shift towards the reactant side. Whenever we are removing PCl3, so remember, when we take away something, equilibrium shifts to the same side to replace what we removed. So if we take away PCl3, which is a reactant, we shift towards the reactant side to replace what we removed. If pressure is increased, so remember, increase in pressure goes to the side with less moles. So I'll put that here. We're going to the side with less moles of gas. So we have to count there are 2 moles of gas on our reactant side, 1 mole of gas on our product side. So this will shift to the right, shift towards the products. If temperature is lowered, so remember, temperature and concentration follow the same set of rules. If we decrease the temperature, we're removing heat from the product side, which means we have to shift to replace what we remove. So this will shift back towards the product side to replace that heat. With volume, so volume goes along with pressure, but remember, if we increase volume, we are decreasing pressure, which means we need to go to the side with more moles of gas, which is our reactant side. Now, if we have neon gas added, sometimes it'll say you are adding something that is not part of the reaction. Might say you're adding an inert gas. Anything like that is acting as a catalyst. So when there's a catalyst, there's no effect. So anytime you're adding something that is not in the reaction, it does not affect your equilibrium position. I do want to switch over and look at some of the equilibrium graphs. So with equilibrium, we saw where you have your beginning amounts and they change over time and then eventually level off. Well, we can graph Le Chatelier's as well. So we can look at if there is equilibrium, we have those flat lines to start with, and then we create some sort of change in the graph. We look at how those substances will change to reestablish equilibrium and flatline again. So let's look at a couple of these. So here I have 3 different graphs, and each of these are going to represent the 3 different changes that can occur, the 3 different stressors. So here we're using the reaction of A plus B produces AB plus heat. So this is an exothermic reaction. Looking at the first graph, if you notice, they are both flatlined to begin with, and then they both change gradually. Anytime you see a gradual change in both substances, it is representing a change in temperature. So we increase the temperature, which is going to shift towards the left, shift towards our reactants. So our product decreased over time and our reactants increased over time. The second graph, notice that that A has like a sudden jump, whereas AB is just a gradual change. Anytime you have one substance that has a sudden jump, that is going to be a concentration change. So here we increased A, and then they both reestablished equilibrium. So one substance has a sudden jump, the other is a gradual change. Looking at the third graph, notice that they both have a sudden jump. Anytime they both have a sudden jump or everything has a sudden jump, it is going to be a pressure change. So notice that we are going to be increasing AB, our product, which is the side with less moles of gas, meaning that this is an increase in pressure. This is one thing where you may have to be able to explain what is happening at a certain point in time throughout the graph. So you're looking to see if both substances have a gradual change, if one has a sudden change, or everything has a sudden change. The general rules for these: if all changes in the graph are gradual, there's no big jump for anything, it is a temperature change. If one concentration has a sudden increase or decrease, one substance has that sudden jump, it's a change in concentration. If everything has a sudden jump, either increasing or decreasing, that is a pressure change. So here, using the reaction of hydrogen iodine producing that hydrogen iodide gas, notice that we have flat lines for all three at the very beginning. Then we have a sudden jump in our orange line. We have a sudden increase in hydrogen, which is going to shift equilibrium towards the right, towards the product. So our amount of reactants will decrease at that point in time, and our product will increase until they reestablish equilibrium and flatline again. So let's look at a graph where it's going to ask us what change occurs at different points in time. So here it says we have the graph below refers to the exothermic reaction of nitrogen and hydrogen producing ammonia. And remember, it told us this was exothermic. So remember, heat is going to be on our product side. It wants to know what change occurs at time 1, time 2, and time 3 on the graph. So we start off with all three at equilibrium, all three flatlined. At time 1, notice that there's a large jump in nitrogen, and then hydrogen and ammonia slowly change. So one large jump means that this is a change in concentration. So we increase nitrogen, which shifts equilibrium to the right. At time 2, notice that everything has a sudden jump. That means that this is a change in pressure. So our reactants are decreasing. Once that sudden jump occurs, that means that we're shifting towards the product side. And then at time 3, nothing has a sudden jump. So remember, that is a change in temperature. So you should be able to look at a graph and recognize what change is occurring at that point in time.